Let's continue ahead and we derive one more equation which is again important using Biot-Savart law, and it's we have to find the magnetic field, that is B, and we have to find this at an axis, and the axis of nothing else but it's a current carrying loop. So it's not difficult, it's simple, but only you need to know the idea how to derive the equation. So how do we derive this equation? We need a diagram, that means we need a current carrying loop, and it's a three-dimensional figure, so you need to be very careful in understanding. I'm drawing this three-dimensional figure something like this so that you understand that how it looks like. So basically this loop is something like this. So this end, let's say, is a small element dl of the length this as L, and this part, actually if you look into this particular loop, it's coming outward. So if let's say that the current inside this is flowing like this I, and this is my I, then we can assume that this part is going inside and this part is outward. So it's like if it's a circle, it would be something like standing like this, and the half part is inside and it's like this. So we are showing this as a three-dimensional figure because using this concept we will find the value of B and at an axis. So let's say that we have a loop, and let's say that the radius of this loop is A. Let's say that we have a point P at a certain distance, and let's say that the distance is x. So let's say we have a point P at which we have to find the magnetic field, that's B. We have a current, we have a small element over here. Let's say I draw the distance from here as r, and let's say that this angle which is made over here is phi. So at point P we have to find certain relations over here. So if you look into this particular diagram, we can take one small element over here, the other small element at this end. So let's say I call this as AB, and here let's say it's A dash B dash. We will find first the field with respect to this small element and this small element, and then we integrate to find the magnetic field due to the whole loop. So the diagram is very simple. Understanding here is essential. So understanding is the important part over here because it's a three-dimensional figure, so you need to understand that how it will, the visualization is very important here. So this dl part is coming outward, and from here I into dl part is going inward, so inside and outside. So very important part to understand here is that this current element IDL and R will always make a right angle with each other. So this particular angle will be always a right angle. This particular angle IDL and R will always make a right angle with each other. So it's like I have the axis which is here, and this is my another axis here. So this angle is my right angle. We are not looking at this particular angle, but we'll look at this angle, not this which is making with A. Let's say A is the radius of my circular loop. What very important part here is that using right hand thumb rule, or I can also use the right hand palm rule, and if I apply right hand palm rule, what it says that my thumb should point towards the current. So if this is my current and like outward, this is the R is my palm, and if I curve the finger, the direction of the magnetic field due to this will be something like this. Let's say it's delta B. Same thing if I do with respect to this, it will be somewhere like this, delta B. So Also one more law, according to right hand palm rule, this angle will be a right angle. So here also this angle with respect to the distance, if I take this distance and this will be a right angle. We need to resolve this delta b and this delta b into the components and we find the resultant field. So to find that, my resultant field may be in any direction over here. So if this is 90, I know I resolve these into two components, this and this. Now we need this particular angle. How do we find this particular angle is? If you look into the value, this is 90 degrees. This is phi. So this particular angle will be 90 minus phi. So this angle is 90 minus phi. I know that this whole angle is 90. So if this is 90 and this is 90 minus phi, this angle will turn into phi. So if you look into the diagram, you will notice that the angles which we got are phi over here. So in the same way, if I find the components for this also, I will get the angle as phi. So if this is phi, this is delta b, I know that my adjacent will be delta b cos phi and here it will be delta b sin phi. If I look at the, due to this particular element and this is delta b, this will be delta b cos phi and this will be delta b sin phi. These two delta b cos phi and delta b cos phi will cancel each other because they are equal in magnitude, opposite in direction. So my resultant will be something like this, acting in this direction, delta b sin phi. So my total magnetic field, that is B, will be integration of nothing else but delta B sin phi. And this is what we have to find. So I already gave you the basic idea what we have to do. Now we will derive the equation and let's see that how the diagram will be used here. And I'll show you the diagram. This is the diagram. I have already explained you everything with regard to diagram. Now let's derive this equation. So how will we move ahead is, first we'll find dB or delta B. So delta B with respect to this particular element, delta L with respect to this particular element, if we look into the delta L, I resolved the component into delta B sin phi and delta B cos phi. So if you look into first from here, I showed you the angle over here is right angle. So my angle is 90 degrees. So according to Biot-Savart law, it's mu naught by 4 pi I delta L sin theta upon r square. But I know very well the theta over here is 90 degrees because the angle between IDL and R is 90. So I get therefore delta B equals to mu naught by 4 pi I delta L upon R square. Since we know the angle, so we use it like this. This is my equation number 1. Now this value of delta B is something like this over here. Same way I get delta B, same value over here with respect to this particular element. So we got with respect to two elements this, but if I keep on taking small elements all over here, I will get the values of the components like this and it will keep on cancelling with each other. So if you look into the final value of B, it will be nothing else but it's an integration of delta B, that is delta B sin phi. You can easily see from here it's a green and the blue arrows indicating this side. So delta B sin phi, one is for this, and for blue it's delta B sin phi over here. These are the two values for these two components respectively. If I take more elements like this, I will get delta B sin phi, more values. So we have to add all this. That's why we integrate this delta B sin phi. Now what value do we know from here? If I put the value of delta B from equation 1, if I take equation 1 over here, I get therefore B equals to mu naught upon 4 pi I delta L r square sine phi. I'm using the value of equation number 1 over here, mu naught by 4 pi I delta L upon r square sine phi. If you look into and you find the value of sine phi from here, what will be the value of sine phi you get? If you take this as a right angle triangle and you find the value of sine phi, sine is opposite upon hypotenuse, so sine phi will be equals to a upon r. So the value over here and few constants when you remove out, it will turn out into mu naught by 4 pi. What are the other terms we get is I a upon r cube into sine. This remains. After substituting the value of sine phi over here, I get this as the equation. So therefore the value of B now will be equals to mu naught by 4 pi IA upon r cube. If you look into the delta L, integration of delta L, that means the integration of this delta L, then I take one more delta L, then delta L, such small current elements, that is only the length of this. I get this as nothing else but it's a circumference. So what is the circumference of a circle's formula? It's 2 pi r. My radius is a over here, so I get delta L over here is 2 pi a. It's the circumference of a circle. Now let's just substitute one more value if we can get the value of r. Can we get the value of r if I apply Pythagoras theorem over here? So if I apply Pythagoras theorem, I get this as r square equals to a square plus x square. So r equals to a square plus x square raised to half. This is the value of a. Sorry, this is the value of r. I substitute the value of r over here. So what do I get this value as? Therefore B equals to mu naught upon 4 pi IA. Let's substitute the value of r, which we got as a square plus x square. This is raised to 3 and we already had half over, so it's 3 by 2 and I have this as 2 pi a. If I simplify all this, I will get the value of B as mu naught I a square upon 2 a square plus x square raised to 3 by 2. So this is the value of B I will get after deriving it. But this is for one loop. So let's say if I want to find it for n number of loops, what we do is that we just multiply this whole equation by n. So if I multiply this whole equation by n, it will be mu naught n I a square upon 2a square plus x square raised to 3 by 2. So actually it would look something like this. If I write the equation, then the equation will be something like, so my equation would look something like this. If instead of a loop I take n number of turns of a loop, which is called as a coil. So basically this may be the equation if I am finding the magnetic field at an axis due to a given coil. So ni a square. But let's say that we found this for an axis. If I want to find the B at the center and at the center of a loop, so if I take at the center of a loop or at the center of the coil, then what should happen? You can see from this diagram is that we found B at this point. So if I bring this point B at the center, that means I will transform this x, which is equal to 0. So in this particular equation, if I take x as 0, I get therefore B equals to mu naught ni a square upon 2. This x is 0, so we get a raised to 2, that's a square into 3 by 2, so square and square gets cancelled, so I get this as a cube. Now if I simplify this ahead, this whole thing gets cancelled and I get this as mu naught ni by 2a, whereas a is the radius of a loop or a coil. So we get such a value for B, and we get this value by using Biot-Savart law. Same thing you can derive using another law which is called as Ampere's circuital law, and I will teach you this in the next class. Ampere's circuital law is much simpler than what we do using a Biot-Savart law, but the use of Ampere's circuital law is to actually minimize the effort for a student. They have found something which is almost has a similar property and the similar concept what you have done in electrostatic, and this is actually analogous to what you have learned called as Gauss law or Gauss theorem. So again, Ampere's circuital law is nothing else but it's a hypothetical statement. So we'll be applying the same knowledge of Gauss law for an Ampere's circuital law, but I'll explain you first what is this Ampere's circuital law, and we'll be using this concept of Ampere's circuital law to find the magnetic field at the center of a coil or a loop or at an axis also. It's very simple when we use that concept over here. It's not difficult. Okay, so there is again one more small derivation. Just now what we did, either you can derive everything to up to here to find B at the center of a loop, or there is another method, B at the center of a current carrying loop. So there is a different thing when we say loop, that is at the center. See, two things. If I am drawing a loop something like this, and this is an axis, I can find, due to the current carrying this loop, the value of B at a point P somewhere which is at some distance, and we can also find the B at the center. To find B at center, there is a small derivation which if you just go through it you will understand is the simple. We have already used that concept in deriving this, but here we have used the concept and we found first for at axis, anywhere on the axis. So it's like I take this point as P or this as P or this P or here, I will get the magnetic field B at a point on the axis. But if I want to find at the center, you can directly derive it without using the concept of axis. Here we found this equation at the center using the axis and everything. In this case you can directly take a loop and derive it. We already know that the angle between the IDL and the loop is 90 degrees over here, using that concept, and the circumference is, let's say I take this as radius as r, 2 pi r. It's very simple derivation. So if they ask you to derive an equation of a magnetic field at the center of a circular current carrying loop, you can do that much. It's only 3 or 4 steps. But if they ask you to derive on the axis anywhere, then you have to use this whole method, and you should remember how to derive along with the diagram and the description what I gave you. Without description there is no mark for the diagram. So 1 mark for diagram and description, 1 mark goes up to the circumference or somewhere here, and then the remaining 1 mark up to the axis over here. So this is how the marks are allocated, and it's not difficult, it's only how you prepare yourself. Hope you have understood so far what is happening in this chapter. We'll meet in the next session. Take care, stay safe.